In this lecture, we will study about the rheological properties of biological materials. It's a part 1. The rheological properties of the solid materials is commonly known as mechanical properties. So they both are one and the same. The rheology is the science which studies the deformation and flow under forces, under the action of the forces. It's from the root word, Greek word rheos, which means to flow. So when you apply forces to a biological material, if it is a solid, it's going to deform. If it is a liquid, it's going to flow. The biological material can be solid or fluid, but most commonly it's somewhere in between. It's probably, let's say like an apple, it's primarily a solid, but it has a huge moisture content that acts like a fluid too. A muscle tissue has more than 80 or 85% water. So biological materials falls in between. So a lot of time these rheological stuff are important in understanding how the liquid flows in a pipe, or how much stress you need to apply a certain amount of deformation. Why do we have to study? So when you apply the forces, the biological material deform, especially the solids deform. The deformation depends on the stress, moisture content, and composition. And in turn, you can use the deformation to quantify a texture of a material, or to study the damage, or to even estimate the strength of the material. So the mechanical properties are used in determining how much force is required to cut or shear, or how much energy is required to mill or grind, let's say, corn into the corn flour, or how much determine the strength to withstand a certain amount of forces. Or if I want to estimate the tenderness of the meat, can I objectively measure that? Or can I objectively measure the textural properties that can correlate with the sensory properties of a material so that I can use it in the quality control? This is a chart. We will see it on the next few chapters. In this chapter, we focus on the solids, which has the elastic behavior. They can be classified as the Hookean or a non-Hookean solid, which we'll study more. The next chapter we study about the fluids. And later we are going to talk about the viscoelastic, which is the fluid solid. So we will revisit the chart again. To begin with, we need to understand what is stress. The stress is given by force per unit area. The force itself is not a very useful criterion because it depends on how much area you apply on. Is it a large force spread across a large area or a very tiny area? That is the stress. So the normal stress means the direction of the applied force is perpendicular to the deforming area. The area that is deforming is this, and it's perpendicular to the area. Okay. So the normal stress, again, stress equal to force per unit area. The key is the perpendicular. Okay. And strain, so when you apply the stress, the material deform. Let's say it deforms into L prime, and basically it deforms by delta L. Then the strain is delta L, the deformation by the original length or the dimension, original dimension. Okay, that's the strain. So it is unitless, no units. So basically the Hooke's law states that the stress is proportional to strain. Higher the amount of stress applied, the more the deformation and more the strain is. And the proportionality constant is Young's modulus or modulus of elasticity, which is the property of a material. This is important. The stress is not a property. Why? Because stress is the force I am applying on a biological material. It's not a characteristic of a material. The strain, even though it depends on the stress, it's the reaction of the biological material to an applied stress, it's still not a property because it depends on how much force I applied. But the stress per unit strain to create a certain amount of unit deformation, how much stress is required, is a property. So to create a unit strain, you may require a less stress for material 1. That means it's softer. For another one, to create the same amount of deformation, you need to apply a huge amount of stress. That means it's stronger. So if you plot stress versus strain, the slope is the Young's modulus. So a lot of time your instruments gives FD curve, where F is the force, D is the deformation or the delta L. But stress is nothing but force per unit area, strain is nothing but delta L by L, and the slope is Young's modulus. So this might be material A, this might be material B, then Young's modulus of B is greater than the Young's modulus of A, and B is stronger than A. Okay. So what are the typical E values or the Young's modulus values? The con, when it is at the safe moisture content, it is 400 megapascal. When it is moist, it's soft. That means it has a lesser value. Of course, the potato is going to be less, and watermelon is really, really soft, so it's really, really low. Here again, I want to distinguish biomaterials and the biological material. Okay, this course focuses on biological materials. The biomaterial is something that is placed in a biological system, say a human body. It could be either synthetic material like a steel or titanium, or it could be a biological material. Whereas a biological material is a living or once living, right? So if you look it up, if you are going to put a rod as a biomaterial in a human body, in a leg, then the strength of the rod should be similar or better than the strength of the rod or strength of the bone. So a biological material, or even for the biomaterial, the strength of the material is an important consideration. So let's try to solve this problem. So the question is, what is Young's modulus? You are applying a force of 20 newtons. You are applying it on a cross-sectional area, which is pi by 4 into 20 square, which is pi by 4 into 400, which is 100 pi millimeter square, right? So the stress is force per unit area, and the strain is delta L by L. The delta L by L is nothing but 0.5 millimeters divided by 20 millimeters, and the Young's modulus is stress over strain, which is 20 Newton divided by 100 pi millimeter square times 0.5 millimeter by 20 millimeters. So you will get an answer in Newton per millimeter square. That's the Young's modulus. You can convert it to Newton per meter square and express it as a Pascal. So when a specimen is compressed, right? When a specimen is compressed, it gets shorter, right? but it get wider, right? So it is expands while it is compressed, right? So the Poisson's ratio, which is a property of a biological material, is defined as lateral strain by the axial strain. The lateral strain, if this is L, if this is B, if this is delta B, if this is delta L, so the axial strain, let's call it as the axial strain, is parallel to the force, which is delta L by L. The lateral strain is on the other direction, which is delta B by B. So the Poisson's ratio is the lateral strain divided by the axial strain. So what is the maximum value of the Poisson's ratio? Like I said, the axial direction is one direction, right? One direction, which is parallel to the applied force. Whereas the lateral directions are two of them perpendicular to the applied force. So you are compressing it on the one direction, but it's expanding on the two direction. Therefore, the maximum value is 0.5. So if material is 0.5, that means the material is complete solid without any porosity, like a complete steel kind of stuff. It's a completely non-porous. And when you compress it, it has to expand on the other direction, so it will be close to 0.5. Whereas if it is like a cork, very porous, when you compress it, you remove the porous space, it doesn't really expand, then this is equal to 0, so at mu equal to 0, right? So if you look at the different values, actually the steel is even 0.3. The gelatin, which doesn't have any pore space at all, which is 0.5, the cork is 0, most other materials fall in between. So let's conclude this part of the chapter and let's record